Good morning, welcome back to our physics classes. Last class we have seen second law of thermodynamics. We have defined the second law of thermodynamics and we have seen the two different statements for the second law of thermodynamics, that Kelvin-Planck statement and Clausius statement. And we have seen both are negative statements. It is impossible to transfer all the heat energy, it is impossible to convert all the heat energy supplied to a system into useful work. That is the Kelvin-Planck statement. It is impossible to transfer heat from a cold body to hot body without the help of an external agency. That is given by Clausius statement. And based on these two statements, we designed two devices, that is heat engine and refrigerator. We have seen what is a heat engine, Carnot's heat engine. We have seen what are the basic requirements for the components of Carnot's engine, and which are the four processes taking place in Carnot cycle, and what is the net process there. All these matters we have already seen. So you can have that PV diagram for our Carnot cycle, in which you are having four processes: isothermal expansion from A to B, and adiabatic expansion from B to C, and isothermal compression from C to D, and adiabatic compression from D to A. So during the process A to B, the temperature remains as T1. From B to C, the temperature falls to T2. Then C to D, the temperature remains as T2. Then from D to A, temperature coming back to T1. Okay. So, what is the net work done in this process? By the PV diagram, it is clear that the area enclosed by the cyclic process is the work done. That is, the area ABCD includes the work done in that cyclic process, Carnot cyclic process. And now you have to find out with the equations what is the net work done in that process. So, first of all, we can say that there are four processes. Two processes is done by the system and two processes are done on the system. Since we are taking in the case of volume, we can say that work done by the system expansion, that is positive, work done on the system is negative. So, one isothermal and adiabatic is done by the system, and one isothermal and one adiabatic is done on the system. So, one isothermal and adiabatic expansion, one isothermal and adiabatic compressions. These are the four processes happening there. See, we can say that the adiabatics are from B to C and B to A. And for adiabatics which are between the same isothermals, that means B to C, the temperature difference is T1 and T2, and D to A, the temperature difference is T2 and T1, which means between two isotherms, which is the if adiabatics are between the same isotherms, the work done will be equal. That means here work done in expanding from B to C is equal to work done in compressing from B to A, which means work done in adiabatics are equal and opposite, they will cancel off. That means whatever work is required to expand, that much amount of work is done on compression. So net work done during adiabatic processes are zero. Is it clear? The reason is these two adiabatics are defined between the same isothermal curves. Okay. Now you have two processes left. One isothermal expansion and the other isothermal compression. One isothermal expansion and one isothermal compression. So work done in expansion you can take it as positive, work done in compression you can take it as negative. So you can define two work done there, that is W1 and W2. W1 in expansion and W2 in compression. The W1 you can take it as positive and W2 you can take it as negative since it is compression. Okay, and moreover, what is this W1 and W2 stands for? So W1 is isothermal expansion. How it happens? When the system absorbs Q1 amount of heat from the source, that Q1 can be used for two purposes according to the first law of thermodynamics, can be used for two purposes: increasing its internal energy and doing an external expansion work. That expansion work is this W1. Remember. Okay, so when W1 you are getting, the reason for that is the system absorbs Q1 amount of heat from the source. But we can't directly say that Q1 is equal to W1 because Q1 can be used for delta U plus W1. What is delta U there? Since it is an isothermal process and our system is an ideal gas, for ideal gas, internal energy is highly kinetic, strictly kinetic. Kinetic energy depends upon temperature. But here, first process is an isothermal process expansion, which means during that process the temperature is not changing. Temperature is not changing means its kinetic energy remains constant, which means its internal energy remains constant. Are you getting that? So we can say that W1 is equal to Q1 since delta U equal to 0. Okay, so W1 is equal to Q1. Now what is W1? W1 is the expansion from A to B isothermally. So we can say that Q1 is equal to integral VA to VB, that is volume at A is VA and at B is VB. VA to VB, PdV. Okay, so W1 is equal to integral VA to VB PdV, which is equal to integral VA to VB PdV. PdV is RT1 divided by VdV. Temperature is T1, RT1 divided by VdV. So when you are taking that RT1 divided by VdV, R and T1 are constant, can be taken out. So this will become RT1 into integral VA to VB 1 by V dV. You know, we have already defined these steps. Anyhow, you can define W1, which is equal to Q1 equal to RT1 log V2 by V1, that is VB by VA. When you are integrating that, the steps are already we defined, so I am not repeating the step. But it will be RT1 log VB divided by VA. RT1 log VB divided by VA. This is the work done in isothermal expansion, which is automatically equal to Q1 since the internal energy change is 0 there. Now you can go for W2. So what is W2? W2 is the heat ejected into the sink. W2 is the work done in isothermal compression. During that compression process, what will happen? Since again it is an isothermal compression, internal energy is not changing. So that work done is equal to the heat energy ejected into the sink. So W2 is equal to Q. W2 equal to Q2. Which is equal to, it is compression. Compression means that work done is negative. Minus integral Vc to Vd Pdv. And one of the property of the integral that we have already seen, if you are having a negative integral, you can interchange the limit so as to neglect this negative sign. Okay, so that will become integral Vd to Vc Pdv. Integral Vd to Vc Pdv. Okay, now what is that? That will become RT2 log Vc divided by Vd. RT2 log Vc divided by Vd. This is W1 and W2. W1 and W2. So when you are taking the ratio Q2 by Q1. When you are taking the ratio Q1 by Q2 or Q2 by Q1, we can take it as Q1 by Q2. When you are taking the ratio Q1 divided by Q2, Q1 divided by Q2 will become W1 divided by W2, W1 by W2. What is W1? W1 is RT1 log VB by VA, and W2 is equal to RT2 log VC by VD. So R is getting cancelled from both terms. So the remaining terms are T1 log VB by VA divided by T2 log VC by VD. T1 log VB by VA divided by T2 log VC by VD. Is it clear? Now we have to find out what is the value of VB by VA and VC by VD. VB by VA and VC by VD. For that, you can consider the adiabatic processes. For that, you can consider the adiabatic processes. So that adiabatic process, we can have the adiabatic equation is P V power gamma, that is P1 V1 power gamma is equal to P2 V2 power gamma, and P is equal to RT by V. PV is equal to RT by V. So you can take this is RT1 V1 power gamma minus 1 equal to RT2 V2 power gamma minus 1. Okay. So R and R get cancelled. So another form of adiabatic equation is T V power gamma minus 1 is constant. P V power gamma is a constant or T V power gamma minus 1 is a constant. Now you can consider these two adiabatics. That means when you are adiabatic expansion, VB and VC are at the same adiabatic. So at the point D, what is the temperature? T1. T1 VB power T1 VB power gamma minus 1 equal to T1 VB power gamma minus 1 equal to T2 VC power gamma minus 1. Is there any doubt for that? At the point B, the temperature is T1 and the volume is VB. At the point C, the temperature falls to T2 and the volume is VC. Now you consider VD and D to A, that is adiabatic compression. When you are having D to A, we can say T1 VA power gamma minus 1 equal to T2 VD power gamma minus 1. Is there any doubt for that? No chance of any doubt. Since it is very clear, T V power gamma minus 1 is constant for an adiabatic process. So what will happen? When you are taking the ratio of these two equations, on the left hand side, T1 and T1 get cancels. VB by VA whole power gamma minus 1 equal to T2 and T2 get cancels. VC by VD whole power gamma minus 1. Okay. So it will be reflecting there as VB by VA is equal to VC by VD. Now we are considering that here T1 log VB by VA is equal to T2 log VC by VD. But VC by VD is also VB by VA. So what will happen to this equation? Q1 by Q2 equal to T1 by T2. So when you are substituting that here, it results here Q1 by Q2 or W1 by W2 equal to T1 by T2. That is an important result. So Q1 by Q2 is equal to T1 by T2. Q1 by Q2 is equal to T1 by T2. Now you can go for the efficiency. Of an Carnot engine. Efficiency of Carnot engine. So how you can define the efficiency of a device? Efficiency of a device is given by, it is denoted by the notation eta. Eta denotes the efficiency, which is equal to output divided by input. Divided by input. Whatever may be the output, whatever may be the input, generally efficiency of a device is given by output divided by input. Here what is our output? Output is W, that net work done, external work done we are getting, divided by what is input, what is the system taking from outside, that is the input. What is actually the system taking from outside? Q1 amount of heat is absorbed from the source. That is actually the input to the working substance. So W by Q1 is the efficiency, output by input. Now you can say that what is this W? W is equal to Q1 minus Q2. What is Q1? Q1 is the amount of heat absorbed and Q2 is the amount of heat ejected into our sink. So the rest of the energy, rest of the heat energy is converting into equivalent amount of work done. So we can have W is equal to Q1 by Q2. So eta is equal to Q1 minus Q2 divided by Q1, which is equal to 1 minus Q2 by Q1, which is equal to 1 minus T2 by T1. 1 minus T2 by T1. What it says or what it indicates? It indicates that work done and efficiency, we can say that efficiency of a Carnot's heat engine depends not on the working substance, not on any other parameters, but it depends upon T1 and T2. What are T1 and T2? I think you are remembering that. I suppose you are remembering. What is T1? T1 is the source temperature and T2 is the sink temperature. Okay, T1 is the source temperature and T2 is the sink temperature. So efficiency is equal to 1 minus T2 by T1. How you can get the efficiency of maximum efficiency? It is not possible to design a Carnot's engine with 100% efficient. Which means if for getting the 100% efficiency, what you have to do? You have to keep Q2 0. You have to keep Q2 0. Then only Q1 by Q1 equal to 1 will get as the efficiency. But it is not possible. It is not possible to convert the energy absorbed by the system wholly into useful work. That is the Cauchy statement. Kelvin Planck statement. That is a Kelvin Planck statement. Okay, so it is not possible to have a Carnot engine with the 100% efficiency, but we can say that suppose we are designing too many heat engines. Too many heat engines between the same source and sink. It is not necessary that all the heat engines are Carnot's engine. You can define any kind of heat engine working between the same source and sink. That means same source is kept at temperature T1 and the sink is kept at temperature T2. But one of these engines are Carnot's engine. We designed many heat engines between the same source and sink, but one of it is Carnot's engine. Okay. So it is found that no other heat engines, listen carefully, no other heat engines working between the same source and sink can have efficiency more than a Carnot's reversible engine working between the same sink and source. No other heat engines can have efficiency more than Carnot's reversible engine when they are working between the same source and sink. Is it clear? That means if you design any kind of heat engine between the same source and sink, but its efficiency will be always less than efficiency of a reversible Carnot's heat engine designed between the same source and sink. And that statement is known as Carnot's theorem. That is known as Carnot's theorem. Okay, so Carnot's theorem is not the basic principle of Carnot's engine. Remember that. Carnot's theorem is not the basic principle of Carnot's engine. Carnot's cycle is also not the basic principle of Carnot's engine. But Kelvin Planck statement is the basic principle of Carnot's engine. Carnot cycle is the process through which the Carnot cycle is carrying out. And Carnot's theorem is an outcome of Carnot's cycle or Carnot's heat engine. Remember, Carnot's theorem is not the basic principle of Carnot's engine. Okay, so that is Carnot's engine and Carnot's theorem. So Carnot's engine we have seen, and what are the requirements, what are the processes, what are the strokes, and what is the efficiency of a Carnot's engine. Remember, it should be a sure question in your question paper. It's a must question from your question paper. Okay, so that much important topic is Carnot's heat engine. Heat engine, second law of thermodynamics especially, and the heat engine or refrigerator, both are too much important in the examination point of view. Okay, so that is the first statement of, that is the Kelvin Planck statement of the that is the second law of thermodynamics, and based on that we have Carnot's engine and Carnot's theorem. Okay, so we will meet in the next class with the second statement of the second law of thermodynamics.